Under acidic conditions, epoxides are protonated. So let's look at this epoxide that's shown. And if this is treated with HBr, for example, or HCl, those are acidic conditions where the epoxide oxygen will become protonated. So we have the protonated epoxide and the bromide or chloride, for example, that gets kicked out during the proton transfer. And then now the nucleophile, which is the halide anion, will do a nucleophilic attack. And when you have a primary versus a secondary carbon, the attack regioselectivity is governed by steric hindrance. So the halide will prefer the least sterically hindered carbon, and it will do an SN2 reaction, breaking that carbon-oxygen bond. And then that produces the product that's shown. Notice the retention of stereochemistry in this reaction. If an epoxide that has a tertiary carbon in particular, right, it's this tertiary carbon that's important. If it's treated with the same reagent, so HCl or HBr, for example, then the regioselectivity of the reaction is different. So we have different regioselectivity when there's a tertiary carbon present as part of the epoxide. So the reaction mechanism proceeds the same way. We first protonate the epoxide, but because of the tertiary carbon, the carbon-oxygen bond between the tertiary carbon and the oxygen is weakened. And that's because the oxygen now has this positive charge, and oxygens don't like to have a positive charge. So if it can weaken this bond, then instead of having a full positive charge, it's essentially like sharing the positive charge between the carbon and the oxygen. And this only works well when the carbon is tertiary, because the carbon has to be able to stabilize a positive charge well in order for the bond to weaken. And because the bond is weakened, now the halide that gets produced in the proton transfer step will actually prefer to do a nucleophilic attack at that more substituted carbon. So now the regioselectivity is no longer governed by steric hindrance. Instead, it's an electronic effect. Essentially, the tertiary carbon has more positive character, and it really attracts the negatively charged nucleophile to it, even though it's more sterically hindered. It's still considered an SN2 reaction, even though it's a tertiary carbon. And we've seen this many times in first semester organic chemistry. So if this was a stereocenter, it would be inverted because it is a true SN2 reaction. So let's look at an example where you have a secondary carbon versus a tertiary carbon. So remember, anytime you have a tertiary carbon, the nucleophilic attack will primarily occur at that tertiary carbon, because after the oxygen is protonated, that carbon-oxygen bond is weakened. So we have, first we have the proton transfer step that we saw before. that will produce the protonated epoxide. And again, this bond now is weakened because the tertiary carbon can help stabilize some of that positive charge. So it really shares the positive charge as opposed to having it fully on the oxygen. As a result, the nucleophile, which in this case is an alcohol, sorry, RO, let's erase that. So the nucleophile is an alcohol, and it will do a nucleophilic attack, again, preferentially on the tertiary carbon when a tertiary carbon is there. It's still SN2, so it undergoes inversion of configuration, which is why you can see that the methyl group here that was down is now up because of that inversion. So initially, the intermediate is protonated. So after the nucleophilic attack, we have the alcohol here, and then we've undergone inversion here. So our methyl group is up, and we have the nucleophile that attack, which is protonated initially, and then it can be deprotonated by another equivalent of alcohol, which leads to the final product. Looks like we accidentally lost some things here, so we'll attempt to draw that back in. So proton transfer produces the product.